US Physics Olympiad, year 2016, USAPHO. Final round. This round consists of two consecutive parts. Part A, which had 4 problems, and part B with 2 problems. For each part they were given 60 minutes, and the solutions for all these problems you can find in the reference of the description below this video. Problem A1. The Doppler effect for a source moving relative to a stationary observer is described by formula F equal F0 over 1 minus V over C cosine theta, where F is the frequency measured by the observer, F0 is the frequency emitted by the source, V is the speed of the source, C is the wave speed, and theta is the angle between the source velocity and the line between the source and observer. Thus theta equals 0 when the source is moving directly toward the observer, and theta equals pi when moving directly away. Sound source of a constant frequency travels at a constant velocity past an observer, and the observed frequency is plotted as a function of time. The experiment happens in room temperature R, so that the speed of sound is C equal 340 meters per second. Question A. What is the speed of the source? Question B. What is the smallest distance between the source and the observer? Solution for problem A1. Question A. If we look at this graph, we can see that on this picture for time equal 0, we have almost 0 degrees theta, and for time 14 seconds it's almost 90 degrees. So we can write two equations. For these two asymptotes we have F1 equal 449 Hz and F2 equal 422.5 Hz. So now we can divide first expression by second expression and find what is V over C. So from here we can find that V over C equal approximately 0.0310, and the speed of the source equal 0.6 meters per second. That was the answer for question A. Question B. Also we can find what is the frequency of source. That will be F1 multiplied by 1 minus V over C, or around 435 Hz. Question B. What is the smallest distance between the source and the observer? Let's take first derivative from this expression. df over dt will be this expression, and in point when theta equal pi over 2, we have this expression. In point theta equal pi over 2, we have df over dt equal negative f0 multiplied by v over c and multiplied by v over d0, where v0 that's a shortest distance for theta equal pi over 2. And from here we can find what is d0. We just need to measure what is the slope of this graph in point for theta equal pi over 2. Finally, for shortest distance we have this expression, and df over dt we can find from graph in a region where f0 equal 435 Hertz, and this will be our approximate answer, 20.5 meters. This is the answer for question B, and this is solution for problem A1. Problem A2. A student designs a simple integrated circuit device that has two inputs, VA and VB, and two outputs, VO and VG. The inputs are effectively connected internally to a single resistor with a effectively infinite resistance. The outputs are effectively connected internally to a perfect source of EMF E. The integrated circuit is configured so that E equal G multiplied by VA minus VB, where G is a very large number, somewhere between 10 power 7 and 10 power 9. The circuits below are chosen so that the precise value of G is unimportant. On the left is an integral schematic for the device. On the right is the symbol that is used in circuit diagrams. Question A. Consider the following circuit. R1 equal 8.2 kilo ohm and R2 equal 560 ohm. Are two resistors. Terminal G and the negative side of V in are connected to ground, so both are at a potential of 0 volts. Determine the ratio V out to V in. Solution for question A. The key idea is that E is finite. Then VA approximately equal VB since G is so large. If we work exactly, then the answers will contain terms like VB minus VA over G, which are negligible. Thus we can find the same answers by just setting VA equal VB. For part A, we will not assume that VA equal VB. Since terminal G is grounded, we have VG equal 0 and VA equal V in. So V out equal G multiplied by V in minus VB. No current runs between A and B, so any current through R1 also flows through R2. Then ohm laws give us equation VB over R2 equal V out over R1 plus R2, which will give us this relation between V out and V in. We just need to express V out through V in. That will be this expression. But 1 over G is very small compared to this part. It means that V out over V in approximately equal this relation, or 15.6. That was the answer for question A. Question B. Consider the following circuit. All four resistors have identical resistance R. Determine V out in terms of any or all of V1, V2 and R. Solution for question B. For this part we will assume that VA equal VB, and again VG equals 0. It's grounded. And if current I flows through the bottom resistor below B and G terminal, this one, then V2 equal to VB. Since the voltage drop across the bottom two resistors must be equal. Similarly, the voltage drop across the top two resistors is equal. So it means that V1 plus V out equal to VA. Then V out equal to VA minus V1 or V2 minus V1. This was the answer for question B, and this circuit is a subtractor. Question C. Consider the following circuit. The circuit has a capacitor C and a resistor R with a time constant RC equal tau. The source on the left provides variable but bounded voltage. Assume V in is a function of time. Determine V out as a function of V in and any or all of the time t and the tau. Solution for question C. We again set VA equal VB equal 0. Then the capacitor charge and the current satisfy these two equations. Q equals C V in and dQ over dt equal negative V out over R, where the second result follows from Ohm's law. Then we have V out over R equal negative C dV in over dt, and finally we have V out equal negative tau multiplied by dV in over dt. This was a solution for question C, and this circuit is a differentiator. That were 3 answers for question A, B, and C of problem A2. Problem A3. Throughout this problem, the inertial rest frame of the rod will be referred to as the rod's frame, while the inertial frame of the cylinder will be referred to as the cylinder's frame. A rod is traveling at a constant speed of v equal 4/5 of speed of light to the right relative to a hollow cylinder. The rod passes through the cylinder and then out the other side. The left end of the rod aligns with the left end of the cylinder at time t equals 0 and the x equals 0 in the cylinder's frame, and time t0 equals 0 and the x0 equals 0 in the rod's frame. The left end of the rod aligns with the left end of the cylinder at the same time as the right end of the cylinder aligns with the right end of the cylinder in the cylinder's frame. In this reference frame, the length of the cylinder is 15 meters. For the following, sketch accurate scale diagrams of the motions of the ends of the rod and the cylinder on the graphs provided. The horizontal axis corresponds to x, the vertical axis corresponds to ct, where c is the speed of light. Both the vertical and horizontal grid lines have 5 meters spacing. Question A. Sketch the whorled lines of the left end of the rod RL and the left end of the cylinder CL, right end of the rod RR and the right end of the cylinder CR in the cylinder's frame. Question B. Do the same in the rod's frame. Question C. On both diagrams, clearly indicate the following 4 events by the letters A, B, C, and D. A. The left end of the rod is at the same point as the left end of the cylinder. B. The right end of the rod is at the same point as the right end of the cylinder. C. The left end of the rod is at the same point as the right end of the cylinder. D. The right end of the cylinder is at the same point as the left end of the cylinder. Question D. At event B, a small particle P is emitted that travels to the left at the constant speed Vp equal 4/5 of speed of light in the cylinder's frame. Question 1. Sketch the world line of P in the cylinder's frame. Question 2. Sketch the world line of P in the rod's frame. Question E. Now consider the following in the cylinder's frame. The right end of the rod stops instantaneously at event B and emits a flash of light, and the left end of the rod stops instantaneously when the light reaches it. Determine the final length of the rod after it has stopped. You can assume the rod compresses uniformly with no other deformation. Any computation that you do must be shown on a separate sheet of paper and not on the graphs. Graphical work that does not have supporting computation might not receive full credit. Here are presented two sheets for your diagrams. Solution. Here we presented solution graphs for this problem. The graphs are shown here, where the yellow line is the particle P and the green line is the flash of light. The final length of the rod is simply the distance between the line CR and the intersection of RL and the green light, i.e. 25/3 meters. There is no need to apply length contraction as we are already in the rest frame of the rod at this point. Nonetheless, the way we have chosen to stop the rod has squeezed it shorter. That was solution for problem A3. Problem A4. The flow of heat through a material can be described via the thermal conductivity K. If the two faces of a slab of material with the thermal conductivity K, area A and thickness D, are held at temperatures differing by delta T, the thermal power P transferred through the slab is this expression. A large flat lake in the upper Midwest has a uniform depth of 5 meters of water that is covered by a uniform layer of 1 centimeter of ice. Cold air has moved into the region so that the upper surface of the ice is now maintained at a constant temperature of negative 10 degrees Celsius by the cold air. An infinitely large constant temperature heat sink. The bottom of the lake remains at a fixed 4 degrees Celsius because of contact with the earth, an infinitely large constant temperature heat source. It is reasonable to assume that heat flow is only in the vertical direction and that there is no convective motion in the water. Question A. Determine the initial rate of change in ice thickness. Question B. Assuming the air stays at the same temperature for a long time, find the equilibrium thickness of the ice. Question C. Explain why convective motion can be ignored in the water. Some important quantities for this problem you can take from this table. Solution. Solution for question A. Determine the initial rate of change in ice thickness. So first, on the border of water and ice, we have temperature must be equal to 0 degrees Celsius. And now, because ice is very thin and water is very thick, so it means that we have rate of power going from this border to upper border of ice much greater than heat going from the ground to the border between ice and water. And this power difference will convert water to ice. And we can write the equations. So first we have power ice, which is going from this border between ice and water, and it's going up, and T0, that's 0 degrees, and T ice is -10, and this is total power. And the other power is going from bottom of water to the border between water and ice, and that's equal to this expression. Here we have T water equal +4 degrees, and T0 again 0 degrees Celsius. Now we can count what is the power difference, which will convert to latent heat fusion for water. That will be delta P equal P ice minus P water, and that must be equal to latent heat of fusion for water multiplied by speed of change of this mass of water to ice, and that's equal to LF multiplied by cross-sectional area multiplied by rate of change of ice growth multiplied by raw ice. After that we can find what is dH over dt. That will be this expression. Here we see that P ice much greater than P water, so we can neglect it. And finally we have this approximately this rate, which is about 2.6 centimeters per hour. This is the answer for question A. Question B. Assuming the air stays at the same temperature for a long time, find the equilibrium thickness of the ice. Solution for question B. Here we can use again the same expressions for power ice and power water, but now they are in equilibrium, so they must be equal to each other. But now we have to find what is thickness of ice and what is thickness of water. They are different, because total mass must be conserved. We have this expression that d ice multiplied by raw ice plus d water multiplied by raw water equal initial d ice multiplied by raw ice plus initial d water multiplied by raw water. So we have two equations and we have two unknowns, and we can find what is thickness for ice and water. Now from these two equations, when we put numbers, we have these two equations. From the second equation we can find that d water approximately equal to 0.1 from d of ice. And when we put this to the first equation, we can find that thickness of ice equal approximately 4.9 meters. It means that thickness of water is about 49 centimeters. That was the answer for question B. Question C. Explain why convective motion can be ignored in the water. In the water, bottom part has temperature 4 degrees Celsius, and we know that water has maximum density for this temperature, and it's reducing when temperature going up to 0. So it means that in the lake we have water more dense when it's closer to bottom, and it means that there will be no convection. So that's the answer for question C. Problem B1. A uniform solid spherical ball starts from rest on a loop, the loop track. It rolls without slipping along the track. However, it does not have enough speed to make it to the top of the loop. From what height h would the ball need to start in order to land at point P directly underneath the top of the loop? Express your answer in terms of r, the radius of the loop. Assume that the radius of the ball is very small compared to the radius of the loop and that there are no energy losses due to friction. Solution for problem B1. First, let's write the energy conservation equation. If angle of loss of contact with the track is theta, we can write this equation, that total change of potential energy equal to kinetic energy of translational and rotational motion, 1/2 mv square plus 1/2 I omega square. And because motion going without sliding means that omega equal v over r, and also for solid sphere we have moment of inertia I equal 2/5 mr square. And finally we have kinetic energy equal 7/10 mv square. So this is the first relation between angle and v square. Second relation is we can count the moment when this ball leaves the track. This happened when normal force equals 0. In that moment, because ball going by circular motion, we have total centripetal force created by projection of gravity force on the n direction, which is mg cosine theta equal mv square over r. From here we can find what is v square using theta and put in this equation. And now we can count what is relation between height h and angle theta. We have v square equal gr cosine theta, and we can put it here and find that h equal this expression, r multiplied by 1 plus 17/10 cosine theta. Now in point of break we have Vx equal negative V cosine theta and Vy equal V sine theta. From these two equations we can find what is total time to travel. We have horizontal distance to travel to point P equal negative r sine theta, which is equal to Vx multiplied by time t. And from here we can find what is t. T equal V over r multiplied by sine theta over cosine theta. Next step is to input this time to expression for total vertical displacement. For vertical displacement we have negative r multiplied by 1 plus cosine theta. That must be equal to Vyt minus 1/2 gt square. Time we take from here and put here. And finally this could be simplified to this expression, 1 plus cosine theta equal gr over 2v square sine square theta over cosine theta. But we already have expression for v square over gr, that will be cosine theta, and we could put it here. We have v square over gr equal cosine theta, and we can put it in this equation, and we have this expression for cosine theta. Now we can simplify it because we can cancel 1 plus cosine theta from both sides, and we have a quadratic equation. 2 cosine square theta equal 1 minus cosine theta, and it has two roots, one negative and one positive. Of course we are interested in the positive. Cosine theta equal 1/2 And now we can put this 1/2 in final expression for h here. And finally we have this answer. When we put 1/2 instead of cosine theta, we have h equal 37/20r. That's the answer for problem B1. Problem B2. Part A. A spherical region of space of radius r has a uniform charge density and a total charge positive q. An electron of charge negative e is free to move inside or outside the sphere under the influence of the charge density alone. For this first part, ignore radiation effects. Question 1. Consider a circular orbit for the electron where r small less than r big. Determine the period of the orbit t in terms of any of all of r small, r big, q, e, and any necessary fundamental constants. Question 2. Consider a circular orbit for the electron where small r greater than big R. Determine the period of the orbit t in terms of any or all of small r, big R, q, e, and any necessary fundamental constants. Question 3. Assume the electron starts at rest at r small equal to r. Determine the speed of the electron when it passes through the center in terms of any or all of big R, q, e, and any necessary fundamental constants. Part B. Accelerating charges radiate. The total power P radiated by charge Q with the acceleration A is given by formula P equal C xc a power n, where c is a dimensionless numerical constant which is equal to 1/6 pi. C is a physical constant that is a function only of the charge q, the speed of light c, and the permittivity of free space epsilon 0, and the n is a dimensionless constant. Determine xc and n. Part C. Consider the electron in the first part, except now take in account radiation. Assume that the orbit remains circular and the orbital radius small r changes by the amount absolute value for dr much less than small r. Question 1. Consider a circular orbit for the electron where small r less than big R. Determine the change in the orbital radius delta r during one orbit in terms of any or all of small r, big R, q, e, and any necessary fundamental constants. Be very specific about the sign of delta r. Question 2. Consider a circular orbit for the electron where small r greater than big R. Determine the change in the orbital radius delta r during one orbit in terms of any or all of small r, big R, q, e, and any necessary fundamental constants. Be very specific about the sign of delta r. Solution for Part A. Question 1. Consider a circular orbit for electron where small r less than big R. For this case, we need to take into account only charge which is inside of a sphere with the radius small r, because for other charge, due to Gauss theorem, we have no influence inside of such shell for what is inside of this shell. So it means that we have to count what is the charge of this small sphere with a radius small r. Charge of such a sphere will be proportional to small r cube, which is q multiplied by small r cube over big R cube. In this case, we have force between this sphere and our electron, and force between electron and this small sphere equal this expression. Now we can count what is the speed. We have centripetal force, which is mv square over small r, equal to force from this small sphere with radius r. And from here we can find what is the speed. Speed equals this expression. And finally we can count what is total period. Total period will be 2 pi small r over speed v, which is equal to this expression. That was the answer for question 1. Question 2. Consider a circular orbit for the electron where small r greater than big R. Now we have sphere with a total charge q, and the force will be just a regular force between point charges q and e, which is this one. Again, we have mv square over r equal this force. And from here we can find what is speed. That will be this expression. And again we have period equal this expression, which is like third Kepler law, where square of periods proportional to cubes of radii. And for the first question we have time is not depend from radius, like for simple harmonic motion. Question 3. Assume the electron starts at rest at r equal to big R. Determine the speed of the electron when it passes through the center in terms of any of all fundamental constants. Here we just need to integrate the path, because we know what is the force. We have kinetic energy mv square over 2 equal integral from 0 to 2 big R from force, which has a different approach inside the sphere and outside the sphere. That will be these two integrals. So after calculations of these two integrals we have this result, and the speed will be this expression, which is answer for question 3. Part B. Here we have to find what are xi and n in this expression for power. And here we have to use a dimensional analysis. Let's do this. Dimension for power equal mass multiplied by length square and time power -3. Dimension for xi, it's q power alpha, c power beta, and epsilon 0 power gamma. For q and c, that's easy to count what is the dimension, but for epsilon 0 we have to use this formula to find what is the dimension for epsilon 0. From this equation we can find what is dimension for epsilon 0. That will be this expression, charge square multiplied by mass power -1, length -3, and time +2. And now we can do equations for these powers. So for dimensions, finally we have this equation. We converted acceleration to L power n, time power -2n. From here we can find for masses immediately that gamma equal -1. Also for charge we have alpha plus 2 gamma equal 0. It means that alpha equal 2. For length we have this expression, 2 equal beta minus 3 gamma plus n, and for time we have negative 3 equal negative beta plus gamma minus 2n. Here we already know that gamma equal negative 1, and we have beta plus n equal negative 1, and beta plus 2n equal 1. It means that n equal 2 and beta equal negative 3. Finally, we have this result. Xi equal q square over epsilon 0 c cube, and n equal 2. And power will be this expression. So that's the answer for part B. Part C. Consider the electron in the first part, except now take into account radiation. Assume that the orbit remains circular and the orbital radius r changes by an amount delta r much less than small r. First question. Consider a circular orbit for the electron where r less than big R. Determine the change in the orbital radius delta r during one orbit in terms of any or all of r, small r, big R, q, e, and any necessary fundamental constants. Be very specific about the sign of delta r. So here we already know how to count what is the power of radiation. We have power equal this expression. We have to count what is the acceleration and what is period. Period was this one, and acceleration equal to v square over r. And we already counted what is velocity. Velocity was this one. Now we can count what is total energy lost by electron for one period. We have a total energy loss equal power multiplied by period. Period we already counted before, and power is this one. Acceleration, it's v square over r, and v is this one. We already counted in previous topics. When we insert everything in this formula, we finally get this formula. But from other hand, we have energy equal kinetic energy plus potential energy. Or we have v square, this one from here, and this is the formula for full energy. And we can write what is the change of this energy when we change radius by delta r. That will be this expression plus force. Force we can count in previous section, and finally we have this expression, and that's equal to our previous expression for delta E, this one. And from these two formulas we can find what is delta R. That will be this part divided by this part, which is this expression. That's the answer for question 1 in part C. Question 2. Now consider a circular orbit for the electron where small r greater than big R. Solution. We still have power equal this expression, but now we have different approaches for speed and acceleration. For period we had this expression, for speed we had this expression, and for acceleration we can count. Acceleration was this one. Now we can count what is the total energy lost for one period. So we have total energy loss equal power multiplied by period. Power is this one, period is this one, acceleration we can count from here, that's this one, and finally we have this expression for energy loss. And again, from other hand, we have energy equal to kinetic energy plus potential energy, and the change of energy equal this expression, which is this one. And finally, when we equalize this delta E to this delta E, we have for delta R this expression, which is answer for question 2. So we did all answers for all questions and all parts of this problem.